Good evening, everyone. My name is Ananta Chandrakasan, and I'm the conference chair for ISSCC. It is my pleasure to welcome our distinguished speaker for the SRP, Professor Lynn Conway. I'd like to begin with a quote by Ken Shepard of Columbia. What we often forget in engineering and science is that innovation and technological progress happens because of actions of people who have personalities, lives, and life stories that influence them and are influenced by those around them. Lynn's story provides a case in point. 2 years ago, next slide please. 2 years ago, the Solid State Circuits magazine ran a special issue about Lynn's work, where we learned about her role as the hidden hand behind the VLSI revolution. If you've not had an opportunity to read so, please read this article. Educated at MIT and Columbia, Lynn joined IBM Research in 1964, where she made major innovations in computer architecture. After completing her gender transition in 1968, Lynn took a new name and identity and then restarted her technical career. She worked passionately inside Xerox PARC while minimizing external exposure, thus remaining a mystery person to those outside. At Xerox PARC in the 1970s, Lynn innovated scalable MOS design rules and architected the most famous text related to VLSI systems in collaboration with Arbor titled Introduction to VLSI System. This book was groundbreaking and introduced the world to scalable design rules, an idea that we leveraged for many generations of design innovation and helped greatly influence the MOSIS e-commerce system for rapid chip prototyping. I know that I have personally benefited from the methodologies introduced in the book and used them in my own PhD and research at MIT. Lynn has since won many awards. She's an IEEE Fellow, a member of the National Academy of Engineering, was recently named a Fellow of the Computer History Museum, and will receive the IEEE RSC James Clerk Maxwell Medal in June. But at 77, what Lynn treasures most are memories of the exciting teams she's joined and adventures she's gone on. Not only on intellectual adventures at IBM Research, Xerox PARC, DARPA, and University of Michigan, but also adventures, rock climbing in Yosemite valleys in the 60s, whitewater canoe slalom racing in the 80s, and motocross racing in the 90s, right till she was 60 years old. Today, Lynn will reflect on the rapidly expanding microsystems frontier and ponder the amazing engineering adventures that lie ahead of us. So please join me in welcoming Lynn Conway.
Thank you, Ananta. And I really appreciate being invited to speak with you this evening. I'm going to talk a bit about our travels through time. It's wonderful for me to return to the Valley and be here with you in these exciting times. And I think you'll all agree we're definitely living in exciting times. But what do you actually see ahead? What is the excitement all about? Do you see obstacles or opportunities? Right now, many at ISSCC see huge obstacles ahead. We're all familiar with these, such as the end of Moore's Law. Remembering Bob Caldwell's keynote at Hot Chips in 2013, this is on everybody's mind as we chase things down into this corner. And then there's the related obstacle of dark silicon. Device scaling and core scaling, multi-core scaling. Everything not only runs out of steam because of the limits of Moore's Law, but also because of the fact that larger and larger fractions of our chips now have to remain dark. And then there's the innovation valley of death. It's a very interesting problem for people in the research community, if you think about all the scattered research efforts all across the whole large microsystems frontier, in basic research, how many of these will actually end up jumping across this valley and ending up being picked up and moved through applied research into products? Or is this somehow kind of an illusion? We're going to talk about some of these things. But the problem is by focusing ever harder against these obstacles, so if you always see obstacles ahead, you tend to push harder and harder against them. Node after node, we're all familiar with that process. It's easy for our huge electronics ecosystem to habituate into making cyclic incremental optimizations and not see ways to break out of the cycle. So how can we break those habits? Habits are breakable, but you have to know you're cycling around in one and decide it's getting to be very repeated before you do that. How do you do that? Well, one of the things you can do is you can just start questioning everything. Instead of cycling around, just start questioning everything you do. Just think about it, ask questions about it. Especially things we take for granted. So, think for example, we're at the International Solid State Circuits Conference. Well, what is a solid state circuit? What is a solid state circuit? Actually, more to the point, what is a circuit? Just interconnected electronic devices? Or, what's a system on a chip? Everybody uses this term. More to the point, what's a system? Now, why do we want it, whatever it is, to all be on one chip? So let's go meta and visualize these things a little bit more abstractly. What do the following circuits and or systems, pick your word, have in common? And there will be a quiz. Professor Arbor. Regenerative radio receiver, remember these? If you're not sure what a triode is, that weird thing down in there, an FET is pretty darn similar, it turns out. Servo mechanism. PLA, finite state machine. Human in the loop, computer interaction. What do these have in common? They all use and employ some form of cyclic feedback. So why do we call them all cyclic feedback systems? Yeah, just a different way of looking at it, kind of going meta. But why are these cyclic feedback systems all explained by incommensurate bodies of expert theory? How did that happen? Radio circuitry, electronic circuit theory. Become an expert in that. Servo mechanisms, control theory. Become an expert in that. State machines, automata theory. Become an expert in that. You know what those are and you can manipulate them. Well, why can't we do all those things? And you can get on the internet now and you go learn all that theory. The gist of it is not complicated if you have a clue as to what the overarching meta picture is. Humans in the loop. Same thing. Human-computer interaction theory. Many of the same kind of things. Different terms, different experts. But if you really get into all these and look at them, you can get the hang of all of it. So why hasn't a widely shared meta-level cybernetics evolved that enables all of us to quickly grasp the gist of each of those things? So that even kids could sense how they do what they do. Let's go look for some answers. To do that, go back to the future. How I got interested in electronics was, as a child during World War II in the 1940s, I experienced the tremendous cultural impact of radio. It was huge. I also began wondering, what were all those things inside there? What do they do? How do they work? By junior high, I sort of figured it out, begun tinkering with this kind of stuff. And in the 50s and 60s, off I went to MIT and then to Columbia. So you see, that's a familiar kind of story from years and years ago. And there's a 1937 Zenith, International Shortwave Red Console Radio. Sat around that, especially in winter evenings, during the war, listening to the BBC, listening to the latest news of things happening in Europe. Think what that does to a child's imagination, especially when you go look inside that thing and see the glowing parts, smell the smells, what are these things? What do they do? Well, you know, the tubes don't last very long in those things, so you're always replacing them. So you have to learn which ones to replace. Well, the ones that burn out, they're not glowing. You look at this diagram, you go to the store and you get the one and plug it in there. But looking deeper, there's this other diagram. What the heck does this mean? Okay. Now, a good way to figure out radios is to reverse engineer the inventions of Edwin Armstrong back to their foundations. Well, there is that one circuit, regenerative radio receiver, 1912. And DeForest had just patented his triode, 1908. And you look at that circuit now, and that kind of stuff is familiar to you. Just stick an FET there instead of that weird thing it is a triode. But then Armstrong went on, and there were tuned radio frequency receivers, the TRS in the 20s. A little more complicated, but you could still kind of figure it out if you understood the regenerative receiver first and followed the evolution. And then there's the superhet in the 30s, like that big zenith. And there you see a block diagram. You have that first before you even try to understand what that circuit diagram was we just looked at. So by the way, are these circuits? Are they subsystems or are they systems? Okay, now how about you, young students today? As children in the early 90s, the grad students today experienced a huge cultural impact of the emerging personal computers. And some wonder, what are all those things inside? What do they do and how are they made? Many learned programming and then tinkering with PCs. And in the aughts and tens, went on to university and grad school. So during your childhood, things like this were already kind of semi-obsolete. You might have found one or got one or had one, but now you can start taking it apart, figuring out what this stuff is, play with it, maybe tinker it with it. And if by then some of the components are bad, you looked at the motherboard's floor plan for this machine, and you can find out which is which, and maybe find something in another machine and swap it out. But peering in deeper, if you look at the block diagrams of the hardware, you saw this stuff. So how did you visualize these things when you were kids and looked at this? Are these circuits, subsystems, a system, many systems? So that's in your background. Now, think about the kids growing up today. Until now, the microsystems being created by this community have been very deeply embedded out of sight and out of mind inside macro things. Smartphones, wearables, autos, drones. But how many people out there in the great unwashed among the public even know what microsystems really are? They've been very deeply embedded in these things. Out of sight, out of mind. Even when enabling astonishing out-of-body experiences as when flying a parrot bebop using an Oculus Rift, which we will do soon. So, you take this thing, fly it around, stereo vision, and it's also your eyes are transported into the sky and you can fly around and look at things and experience this out-of-body experience. Thinking, wow, how is this doing this? But having no idea of the enormity of the microelectronics that's in that thing. That's all going to change because of Motorola's Project Arbor and other things like it, but especially Arbor, to create modular smartphones. So this is coming. Because Arbor's phone blocks will popularize the emerging concept of hardware apps. So kids everywhere, adults will be lying, but kids everywhere will start noticing and wondering about what all this tiny but empowering stuff is in these things. What are these things? How do they work? What else could they do? Think about it. Such visible hardware apps are going to be composed of a lot of things that are familiar to people here. There's IMUs and sensors and microcams, along with their microcontroller units and all sorts of new interconnects that are emerging across various different kinds of physical connection, wireless, and so forth. And they'll be embedded all across macro-scale systems by exploiting innovations in woven and printed near-field wireless communications as we see in a lot of things, the new Bluetooth beacons by Estimo, the microchiplets work at Park, near-field communications, smart textiles, the Pastor work in Europe. Now, these innovative micro-hardwares are also going to feed back into additive manufacturing, such as when enabling 3D printers to digitally make more powerful 3D printers. So you have a 3D printer which makes another 3D printer using different source code file that is designed to exploit some emerged micro-hardware app that can be plugged into it. I think you can see where that's going, like self-compiling compilers. So surrounded by smartphones, cool robots, animated drones, visibly composed of tiny modular parts, these kids will begin to wonder, what's all that tiny electro, opto, chemo, bio, mecha stuff? Especially as the tiny microsystems are increasingly mapped out in what you might think of as circuit diagrams. Some will learn to tinker, go on to university and grad school. Now here's the key point. Among them are the young folks that as you get into mid-career, you'll be leading and guiding to create the future. So you see, you need a feeling for what this next generation coming along is experiencing, so that you are culturally tuned into how to reach them, how to understand what drives them and what they're thinking about. But what do they think of as a circuit and as a system? Or you see, are such words now constraining our intergenerational thinking? See, we use words that we have learned as we become experts, and we keep reusing them. But maybe we should pop up a level every few years and reframe some of our conversations so as to be more integrative. So to glimpse where this is all heading, check out this Xeno drone. It's a recently launched animated system. This thing's pretty cool. It fits right in your hand. It's another drone, but quite a bit to it. Extremely tiny. It includes an HD cam, IMU, GPS, microcontroller unit, and IR obstacle avoidance, gesture control, auto following. You can put this thing up there and program it to follow you around with a given orientation and altitude and so forth. And then you just start walking around, it follows you around. You know, the ultimate kind of selfie video. And swarming. Since they can do IR obstacle avoidance, you can put swarms of them up there and they'll avoid each other. All right. And more. So now think about the group experience of having your eyes remotely passed off to where you're looking through one of many drones, and you're seeing out of it, and all your friends are in the other ones. This stuff's all coming. You see, it's just all happening. There are so many dimensions to its capabilities, it's hard to even say where the system begins and where it ends. Now, just imagine the impact when today's kids start peeking inside nanodrones. Especially when they start looking at circuit diagrams. What is all this stuff? And at the same time, while they're plugging and playing with stuff like the new, just bounced out of the Kickstarter stuff, the Sam Labs wireless microsystems. They innovate their own animated microsystems. You have to check this out. These are little modular microsystem components that wirelessly connect, so you don't have to wire them, and you actually hook them up by sketching their connections on the computer. That connects them wirelessly. And then you can use those to animate various things. So kids are going to be able to right now begin doing that. Now it's clear that many innovative circuits are involved in providing a Xeno animated system with as many capabilities. But these aren't simply solid-state circuits. They're compound opto, electromagnetic, inertial, mechatronic, and human-in-loop circuits involving multi-physics componentry interconnected to provide multidimensional animated behaviors. So now you get a glimpse of the breakout that's coming. Microcomponents and systems will be innovated by a new generation that you'll be leading who grasp the gist of multiphysics, multiphysical circuitry, and multiphysical systems engineering. And that's going to generate a really rapidly expanding wave of innovations as hinted by the new Myo gesture control armbands from the mechatronics folks at Dalmic Labs. These are folks at the University of Waterloo who've got a really great startup going. And what this is if you look at the armband, and you probably can't see the screen behind it, but those are signals from the movement of muscles in your forearm, which control all the movements of your fingers and your forearm. So that, as you take two of these armbands and put them on your arms, you can actually generate the signals that would operate in a sense, a complete, more or less accurate follower simulator of what your arms are doing as they gesture. So you can look at that in the screen. Now imagine this. You look at that middle screen on the bottom. Here's some simulated arms out there. And here are you with your Oculus Rift on. And in there, as you move your arms up, you see them not in video, but the simulated, actually digitally orchestrated movements taken from the signals in your muscles, projected into another place. So now you start to see where this is going if you connect it back to the other stories. Well, how is this full breakout going to take off? What will be the new multi-engineering methods? How will they be evolved and learned, shared? What infrastructure will be this breakout? How is it going to impact demands for innovations in microfabrication circuits and systems? How rapidly will it exponentiate? And what new technosocial ecosystem will emerge? Let's go back to another breakout. During the VLSI revolution, as early MOS fab technology wrote Moore's Law, and by leveraging the emerging network personal computing, there's many years ago at Xerox PARC and after the ARPANET back then, a cluster of innovations triggered a breakout. Included a set of scalable design rules, and the design and engineering have a set of simplified, restructured design-level abstractions and design methods, along with key open-source cell design examples. These methods were evolved and propagated via new courses. The first one at MIT in 1978. And operating on that pattern and exploiting innovation in e-commerce digital prototyping infrastructure, were used to orchestrate a big internet happening called MPC 79 out in that ARPANET. So here's the circuit diagram of a very early e-commerce system, special one. And here is the environment in which the happening occurred. So what MPC 79 did was it provide a large-scale demonstration and operation and validation of the design methods, circuits, tools, and prototyping technology, triggered gain and an exponentiation of the budding VLSI design ecosystem. So here's a diagram with feedback in it, showing how design prototypes influenced everything that was being developed. What that did was it broke through the VLSI complexity barrier, spawned the Moses surface. We directly transferred the technology from PARC to ISI, and bootstrapped the fabless design and Silicon Foundry paradigm, got people beginning to operate in that environment. So if we take a deeper look at this nested set of circuit diagrams, and I'm still using that word, but think about them in the sense that I've used this in these other technologies that are emerging. The question now is, can you reverse engineer how the VLSI breakout was animated? See? I was told a story about radio engineering, how to reverse engineer what Armstrong did. Can you reverse engineer how this was occurred by looking at the circuit diagrams? You see, we're using similar words to talk across a larger space now, but there's some similarities. There's some eerie similarities to the spaces. Think about that regenerative circuit in its day. Bigger question, could similar circuitry be used to animate future breakouts? like the one that's coming. So, again, exam time. For this, to answer these questions, one hint is to really study and look at this key circuit diagram to see if you can figure out what the heck that means. And also explore some technosocial insights that have been gained since then. Okay, now to finish up, let's go back to the future one more time. This time to now. This microsystem applications revolution is getting up a really big head of steam. In Silicon Valleys, Cambridges, and Maker Valleys all around the world. This is really starting to happen. The kids are doing this stuff, and they're coming, and among them will be the future young folks that you'll be leading when you're at the peak of your careers to change the future. You can see it unfolding in mappings of specific microsystem technology areas. You've seen things like this. You're going to look at all the little deep corners of this and see the process, especially if you go year to year and watch the flow. And in the movement of waves of technology across Gartner's hype cycle. I don't know if you're familiar with Gartner Research's hype cycle, but this is a wonderful sort of moving wave study that is put out each year that shows all of the various technologies in development as they go through from innovation trigger to the peak of inflated expectations to the triumph of disillusionment to the slope of enlightenment and to the plateau of productivity. And you'll find a lot of favorite technologies, and they move at different rates. Some will run this whole thing, the plateau is reached in less than 2 years, some 2 to 5, some 5 to 10, some more than 10, and of course, some are obviously before they ever get there. So that's another way of looking at it. But how could a breakout really take shape? What forces will shape the emerging multi-engineering methodology? And there'll have to be something like this. How will the new methods evolve, be framed and learned? What infrastructure will mediate the breakout? And how could it help trigger and quickly exploit major innovations in microfabrication, microcircuits, and microsystems? And how rapidly will this process exponentiate? And what new technosocial ecosystems will emerge as a result? These questions frame the huge opportunity space ahead. On the other hand, whatever happens, the incoming microsystems revolution will present many challenges to traditional technical culture because of its large accumulation of past habits. And I think this is a really important question. What's the new game? Who gets to play? Will you be involved? How do we team up? What rules do we play by? Where can we turn for guidance? Well, for some great guidance, I find these words from Keith Yamamoto in Science especially interesting. Now think about this. What if baseball were organized like science? Aspiring catchers or shortstops, like students of physics or molecular biology, would be trained by professional counterparts, and top prospects with dazzling skills would turn pro, without learning that by combining their specialized talents, they could create an entirely different game. Managers, owners, and marketeers think the big corporates would seek and reward individual stars at each position, but would not facilitate or nurture a team culture or even a team game. In science, traditions, policies, and bureaucracies isolate disciplines and the discoveries of technologies, squandering exciting opportunities to be empowered by merged ideas and efforts, in short, by teamwork. So the bottom line, as Keith puts it, is it's time to play ball. So, reflecting on our travels through time, I'm reminded of the words of Winston Churchill: the farther backward you can look, the farther forward you can see. Mm-hmm. And finally, reflecting on all that, the words I'd like to leave with you. If you want to change the future, start living as if you're already there. So thanks again for inviting me. This has really meant a lot to me to be here. And I want to wish you all great fortune in the adventures ahead. Thank you.